Before starting to start the videos, in the previous one, I didn't turn on my microphone, so the sound is not recorded. So today I will talk about the Boltzmann equations in the rhythms of the cosmology. Originally, the Boltzmann equations is the uh, dynamics, which is the describe the non-equilibrium thermodynamics. In the cosmological point of view, the number densities of some specific particle species may not follow the equilibrium density. It is called a non-equilibrium state, and these situations are governed by the Boltzmann equation. And there are many examples in the early universe. Uh, there are two well-known examples. One is a neutrino decoupling related with the wave interactions with the pyramid constants. And the second example is the weak interacting massive particles, so-called WIMP, as the dark matter's candidate. And also there are several many topics to describe by the Boltzmann equations, like as the BBN and the CMB, as evidence to sort of the Big Bang theory, and the unknown extremely early universe, like as the baryogenesis and the impulsion theory. So starts from the Boltzmann equations. The is given by the following form. The left hand side is given by the Liouville operators, and the right hand side is given by the Collision operators. And those operators act on the distribution functions f, which is defined on the space x and the p. In the left hand side, Liouville operators so related with the trajectories of the distribution functions over the space. In the non-relativistic versions, the operator L is given by the derivatives of the time and the velocity and accelerations with the chain rule. And if the right-hand side is zero, collision term is zero, then the automatically the distribution functions have the trajectories with the constant is called the free streaming. So no collisions with the other particle, and such a free streaming occurs in the universe like as neutrino. And as a relativistic versions, the Liouville operators given by the Bohr momentums with the tensor index. And in the second term, there will be the gravity effects, which is the relativist versions of the force as a derivative of the matrix. This is the Christopher symbol. And if we insert the FLRW matrix and the homogeneous and isotropic distribution function, then only the time derivatives remains, and the Christopher symbols becomes the Hubble parameters, and also the time components of the Bohr momentum, which is energy remains. So in the left hand side, the equations become such a form: time derivatives and the effect of the expansion. These terms can be obtained by integration by part. And here we integrate the distribution functions over the space so that obtain the number density in the left hand side. And the remaining right hand side, the such integration of the space remains with the collisions operator. So and let's turn to the right hand side, the collision term. If we consider the following scattering process, initial state contains the specific particle psi, which is our interest, and the particles A and B, and the other particle I and J. We will focus on the one species of the psi. Then the such collision operators given by the following form. First of all, this is a phase-space integrations, which is defined through the degrees of freedom Z and momentum P. And in the second line, this represents as the energy conservation divided by the function. And such a collision terms gives the amplitudes, which is coming from the Bellman diagram for the specific process, this scattering process. So the first terms given by the process from the initial state to the final state, but the second terms given by the inverse process from the final state to the initial state with the minus sign. And the initial state gives the distribution function, but the boundary state gives the 1 plus minus distribution functions, which is plus for the bosons and minus for the development case. And as simplifications, for the CP invariance or time invariance case, the amplitudes for the original processor and the inverse processor are same, but as count examples, in the baryogenesis, the CP is a baryolytis, so that the simplification is not valid. And we will consider the limit of the Maxwell-Boltzmann distribution functions as a classical limit, not the Boltzmann-Einstein or parameter statistic. So distribution function gives just 1, and the form of the f is given by the exponential sort of the Boltzmann factors with the chemical potentials of the mu. And we will define the co-moving number density by dividing the entropy density, since the entropy is a constant if there is no additional entropy injection. So the such a co-moving number density becomes the constant if there is no additional entropy injections or photon dilutions or the additional generation of the case of the particle specific size. So the even those the universal expanded co-moving number density y become constant if there's also if such a no additional process for the entropy of the particle productions. So left hand side, the originally there is the expansion factor with the Hubble parameters, but if we define such a y, then the from this and constant entropy, if we derivatives of the time, then this gives the derivatives of the y co-moving number density. And also the we will define the parameter x, which defines sort of the m over the t. T is the temperature and m is the mass of the particles of interest, replaced from the time. We know that the relation between the Hubble parameters and temperatures and the scale factors a at the time. So the relation between the time and temperature is given by the such a form. Then original Boltzmann equation become changes to the dy dx form, and there will be some additional constant from the changes of variable given by the G star, which is the effective number of the relative degree of freedom, and the Planck mass, which comes from the relation between the Hubble parameters and temperatures. So, and now we will apply the Boltzmann equations both for the case of the breathe out. Qualitatively, the abundance follows equilibrium, so number density of the equilibriums are given by the such a form. In the non-relativist case, for the massive particle, it gets the Boltzmann suppression. But after the decoupling, if the interaction rate is smaller than the Hubble expansion rate, around when the temperatures becomes below the particle mass, then the interactions are effectively stopped, and the abundance of the particles will become fixed. But this is collectively decoupling, but to obtain is the exact abundance of the particle which should solve the Boltzmann equation. We will assume the stable particle that at lifetimes of the particle size is longer than the universe time, and there will be an annihilation process by scattering psi bar go to the other particle axis bar with antiparticle. Then the originally in the Boltzmann equation there is such a practice, but the fx given by the such a exponential Boltzmann suppression practice, and the x and x bars are in equilibrium, so there are no chemical and there's no chemical potential. So the second term fx and fx bar factors become such a form, and by using the energy conservation from delta function, the exponents can be replaced by the energies of the psi and the psi bar with the equilibrium case. So the fx bar can be replaced by the such a form. Here is the multiplication. So the second term can be replaced by the number density of the precise and equilibrium density. And if we integrate the amplitude through the pi space, this gives the thermal averages through the non-elation cross section through the psi. So this is given by the sigma v over the averages thermally. So this gives us such a Boltzmann equation form, which can be interpreted as n sigma v is similar to the gamma. So that this gives the decay light and n minus n equilibrium form. And if we replace the variable from the number density to the moving number density and the time to the absolute temperature, then the Boltzmann equation has the following form. Also, if we consider the more simplifications here, then defines the interaction light gamma as the multiplication of the equilibrium number densities and the thermal averages of the light cross section. Then the light hand size is given by the gamma over the h. So if the gamma over the h is extremely smaller than the 1, which is after the breeze out or decoupling, then the light hand size is equal to 0. So the abundance of the y becomes constant. So this is the behavior. So abundance is originally the parallel equilibrium number density. When the temperature becomes below than the mass, then the x is larger than the 1, then the particle becomes non-relativistic, and when the gamma is smaller than the h's, then the particle decouples, so this breaks down, and the abundance are fixed, and because it's a level plus the y moving number density becomes fixed, and this is the moment of the freeze down, the x up. We can divide sort of the case by case. This is the case of the bridge out with the correlated case. If the bridge out occurs in the relativistic case, it is called the hard lyric. So the x out, the bridge out moment, is smaller than the 3. So the bridge out temperature is larger than the mass. Still, the decoupling occurs are still relativistic. So the x out is smaller than the 1 here in the relativistic case. But if the x is larger than the 3, then the bridge out temperature is smaller than the mass. So this case, non-relativistic case, the bridge out occurs non-relativistic case. So this is the core lyric and hard lyric. So well-known example of the hard lyric is neutrino. The neutrino mass is sub-electron volt, but the decoupling temperature, bridge out temperature, is almost a mega-electron volt. By considering the Bernoulli constant with the interaction light and Hubble expansion. But the WIMP case, the its mass is TB, and the result is slightly smaller than that. So there is a well-known example quarterly. There's some terminology issue. In the dark matter, we call the cold dark matters, which is a result relativistic, and this gives the slow velocity distribution, and the free streaming length is not so big at the metal radiation equality, so that it does not erase the anti-block junction. But in the if the active neutrino is the dark matter, is the case of the hot dark matters. It is a relative particle at the decoupling moment, and the velocity distribution is too fast, which might erase the anti-block junctions and the impacts of the power spectrums. So the hot dark matter is already excluded there. So here is the neutrino double electron volt. At the matter radiation equality, temperature is too large at the freeze out case, and still faster it makes a hard lyric. But the WIMP can explain the cold dark matters. So the cold dark matter is slow enough at the structure formation, and this bound is given by the 10 CV. For the hard lyric case, the some equilibrium, the abundance at the breeze out, it can be explained by analytically by the Boltzmann subtraction factor. So by the covering number density, we can obtain the number density by multiplying the entropy density at the current stage, and another density can be obtained by the multiplying the mass of the particle, and we can obtain abundance, capital omega psi, with the Hubble small Hubble parameters. This density parameters can be obtained by the relative energy density of the precise and critical number density. And by that, we can obtain the upper bound of the neutrino. Because omega psi h is given by the such a function, if active number of the degrees of freedom, the random mass of the particle, and this should be the smaller than the 1 to match the observational result. So in the neutrino case, the effective numbers G star of the entropy and the relative degree of freedom is 10 and 1 respectively. So the neutrino should be smaller than the 100 electron volts. But this is weaker than the semi-bound. But the gravitational case, it decouples early, so the entropy is effective numbers are larger than that. So the upper bound is slightly larger than the neutron case. It's a electron. Such a Boltzmann equation can be applied to the various ones, like the impulsion and the baryogenesis, but here so we only discuss the hard relics and the cold relic, and also we summarize the terminologies through the hard and the cold dark matter together.